Good evening, everyone. So, welcome to the fourth week of online discussion on the topic water and wastewater treatment. This is being taken by Professor Prakash from IIT Roorkee. My name is Manitam Prakash. I'm here uh, for my TA duty as a PMRF TA duty. I'm from IIT Kanpur. So generally, we used to meet on Tuesday, but due to some work, I have to reschedule it from Tuesday to Saturday. From next week, the session will be on Tuesday only. That is from 7 p.m. to 9 p.m. The link will be shared to you via NPTL. and we will meet, we will be meeting via online Google Meet using the same link which is being shared to you every week, and all the video uh, live this video is being recorded and it will be uploaded on this YouTube channel. So you can either search my name this Manyatnam Prakash, you will get it, you will see this picture, or mm, or also you can search water and wastewater treatment NOCC 39 week 1 week 2. From there also you can get it. So we are on the uh, big four of the lecture, where these five topics were discussed, that is design of the primary settling tank PST. This has been discussed in week 3 also. In week 3 it was discussion was not so in detail way, but in this week a detailed way, the design was discussed in very detailed way. Biological treatment, that is BOD and nutrition removal, different ways to remove BOD from the system. And I hope from week 2 we have discussed about what is this BOD and what is this nutrient level in the wastewater. Then we discussed about ASAP, activated sludge process, that is also refer as analysis of biological removal process. The biological removal is the biological removal, whatever kind of biological removal we do in water treatment, we do with the help of activated sludge process. So we discussed about this. We'll be discussing uh, 2 3 questions from this topic. Then we have this again, activated sludge process, material balance for aeration basin. Then finally oxygen transfer types and basic principles. Okay, so all these thing has been discussed to you in your lectures. I am here for some of basic questions concept which might be useful to you in your upcoming session, upcoming Qs, yeah, wherever you appear for any kind of exam or anything. So that this is the big. So let's move, and I will discuss each and every question one by one. Apparently, no one is in the session, so I have to move forward because my session is from 7 to 9 p.m. I will go slowly so that if someone want to join, I can recap it. If not, then I will keep going on. The first question is, the grit and sand particle are usually removed from wastewater by which of the settling? And the option are flocculent settling, discrete particle settling, hindered settling, compression settling. So to answer this question, first you should aware of something basic things like what is this grit particles, what are the different unit, then what is this different kind of settling that happens in wastewater treatment plant, yeah, normal treatment plant. When we talk about this discrete settling, hindered settling, compression settling, we generally talk about wastewater treatment only. So by default, you should understand that they are talking about wastewater. So you must have been you must be aware that there are four treatment uh, uh, treatment procedure, that is preliminary treatment, then primary treatment, then secondary, then advanced. So what happened that everyone is aware that in preliminary treatment we try to remove the larger particles, then it will pass, then larger particle, then bigger particle, coarser particle, the size that first we pass through a screening chamber where we remove the larger particle, then the water passes through something called grit chamber. What happened that grit is a small part. um, Grit, by definition, you can say that what is grit? Grit is a small sand particles, yeah, finer rocks, or you can say and it may not be just rock, it can be of any type. Okay, then after grit chamber, they passes through different unit like uh, primary sedimentation tank, then biological unit, and finally filtration and all these things. Okay, so I will the question is here, the grit sand particles. Grit sand particles are the small particles which is present in our wastewater, mostly in inorganic form. This, remember, this grit is in inorganic form. Okay, so first, with the help of a screen chamber, we have removed larger particle. Now it's time to remove the uh, smaller particles which is there in the wastewater. So that can be removed. Generally what happens, that will settle down in your something, a tank known as grit chamber, and the process is called sedimentation. The process in which suspended solids are allowed to settle naturally by the action of gravity. The main thing about this removal unit is that there is no external power or external mechanism is applied for removing it. We just let the water to stay in a great chamber. It will settle down on its own with the help of gravity. Okay, so what will happen, that this everywhere you are seeing this settling. This settling is commonly referred as sedimentation. So this sedimentation can happen, means this is general term, like if something is from something is there and it will settle down naturally by action of gravity, then that process is known as sedimentation. Okay, so generally there are four type of sedimentation. Hello Prashant, welcome to the online discussion. I have already started. This is the first question from Big Four. So the first question is this thing. I was just discussing what is this grit and sand particles and what are the different kind of settling. So there are generally four kind of settling, and settling or sedimentation you can define in this way. This is a normal process, like the process in which suspended solid allowed to settle naturally by the action of gravity. Different type of settling are first is known as type 1 settling or discrete particle settling. So what will happen, that in this kind of settling, suppose this is your chamber, in uh, consider this as your chamber. So what will happen, that it will contain some wastewater. Okay, and obviously it will contain some I'm sorry, I'm not good at this, so I won't be using it. So, eraser. Hmm. Sorry for the inconvenience. Now consider a tank. Consider a tank. It will contain some wastewater. That wastewater will contain some grit or sand particle, which will have its own weight, because that will be not, won't say heavier, but it will have some weight. So what will happen with time, when it will stay in the settling, when it will stay in this grit chamber, what will happen, that it will start to settle down. So what is the main point in this settling? What will happen, that a particle which is there will settle down on its own. It won't be depending upon the other particles. So that's why there is two terms. Type 1, because it is a very normal type of settling. The discrete means one particle is not interfering with the other particle. One particle which is there in the system, it will settle down on its own and it won't interfere with the other particle. So whenever you are observing this kind of settling, you will say the type 1 settling. So how this type 1 settling is means this question, in which kind of system or in which kind of system this settling might happen. So generally this happen with suspended solid which is there in the system. What will it will just lie, the water will pass in the grid chamber, that particle will settle down on its own. Then that is type 1 or discrete particle settling. So from already I have said you the answer that for if at discrete and sat particle will have some own will have its own weight, so it will settle down with some gravity. So the answer of this question is this discrete particle settling. But I will also discuss other type of settling, that is A, C, D. I will just go through the definition, and in the last I will just also discuss the different type of equation involved in discrete particle settling. Okay. So the type 2 settling is flocculent settling. So what will happen that now there will be some suspended particle, a colloidal particle which will not settle on its own. So what will we do that we will add some kind of chemicals. So by adding that chemicals, it will change its property. Now initially that particle might be positively charged or negatively charged. So by adding some chemical, that particle will reverse its characteristic depending upon the pH of the system. And what will happen that other particle which is around them will get attracted to them, and they will form a bigger cluster. Now in discrete particle, what was happening that they were having their own weight, that's why they were able to settle down. But in this particles, the suspended solid don't have sufficient weight to settle down on its own. So I am adding some chemicals. So what will happen that the neighboring particles uh, uh, will attach on the surface of the particle which has changed their nature, and it will form a larger flux, and that will have on doing so its weight will increase, and again that particle will settle down in the system. So that kind of settling where you add some chemical to settle, to make some kind of settlement, that is known as type 2 settling. Okay. Coming down to the third type, that is hindered or zone settling. So what will happen that this is similar to this only this kind, but also this I told you there is, that thing is this thing is happening in this discrete settling was happening in grid chamber or screen chamber, or there is something called primary sedimentation tank if you are not adding any kind of chemicals. This kind of settling happens in coagulation tank या floculation tank. So I hope you are aware with the coagulation of floculation tank. So in that we add some chemicals, we mix, then we let it settle. So in that kind of tank this type 2 settling will happen. Then come hindered settling or zone settling. So first read what is this hindered settling. Hindered settling is when particles in a group slow down each other as they fall through a liquid, making the process of settling longer than it takes if the particles were alone. So what will happen that this happen in this your biological treatment unit. So suppose there will be some organics in the system which won't settle on will which will settle, but it will settle slowly. So what will happen um, that a small particle will first somehow get by some process, be used in activated sludge process, with the help of microbes. What will happen that uh, um, that particle will go down, and it will the process will be very slowly. So what will happen that when we add some microbes to you, when you will see this type of settling, now you will see that every particle is settling in some kind of layer. So previously what was happening that they were settling in on their own at their own position, or by joining other particles. But in this in this method you will see that there is a layer, that's why its name is zone settling. So a kind of layer will be there. In last I will show you the picture also how this zone 3 settling happens. The last is known as compression settling. It's also happening in your biological treatment unit. So in this compression means what happened that you are compressing something. So what will happen that in biological treatment unit the particle which have larger size will settle down, but the smaller won't settle down on its own. So what will happen that when this larger particle will settle down, it will compress the particle which has lower size. So along with larger particle, the smaller particle will also settle down. You can see that from the definition it's clear. The mechanism of settling in is forcing out the water from solid due to compressive force of solid on the top. So what will happen? The particle which is uh, larger in the size or heavier in the size will compress the particle which is lower in the size. Okay, so in that way it will settle. So these were four different kind of the settling. The coming to the our question, the grit sand particles are usually removed from wastewater by which of the settling? The answer is clear, that is discrete particle settling. Okay, so these were discussion. My final answer is option B. Now the question I want to, if coming before going to the next question, I want to discuss something related to this discrete particle settling. So if you have paid attention to the discussion, I said this term that each particle will settle on its own. Other particle won't hinder it or won't interfere in its settling. So now consider this as this whole as a system on which there are many particles like this, and I'm considering a spherical in the nature because um, this will face minimum drag force and all this. This is another question. There is separate question. If you have attended last week, there was one question why in discrete settling we consider a spherical solid, not another other shape. So there is, that is another thing. Okay, so in discrete particle for derivation, we have to, what will happen that it will settle with some kind of velocity. Now, as soon as particle will go in the this primary sedimentation tank, yeah, any grid chamber, so that particle will start settling. So when will it start settling? That the velocity which it attain is known as settling velocity. Our main target is to find the settling velocity. So consider this solid. On this solid, there will be three kind of force. First force will be its own weight. Second force will be buoyancy force, and third force will be drag force that will be on the surface of particle. The weight of the particle will be given by volume into its density. The buoyancy force will be given by volume into density of the water, and the drag force is for any kind of solid, any kind of particle is given by or in any in water or in any liquid. This density will, for other liquid this density will be changing, but the drag force is simple formula is 1 by 2 into drag force coefficient into density of liquid into velocity into projected area means how much area is projected on the surface. Okay, so this CD by drag coefficient, the density of the water, and this okay, and v is the velocity. So now this particle is settled. So at there after some time it will achieve its equilibrium. At that time what will happen that all the force will be equal to each other, means upward force will be equal to the downward force. So that means if we sorry, did I write something wrong? No, this, if buoyancy force plus drag force will be equal to the weight of that particle. So that at that time what will happen that there is no net force is zero, means that particle has achieved one constant velocity. That velocity is known as settling velocity. Okay, I will be putting down all the value 1 by 2 CD. This is the term for coefficient, drag force, this is its weight, and this is buoyancy force. And I will be taking out something common, this 4 by 3 pi r cube. This is this thing I have already discussed in big one also, miss. I'm just recapping it because next question is related to this thing only. Okay, So again taking common, and I know that this density of water can be written in a specific gravity term. After substituting also, and also this velocity will be considered as settling velocity, and this gamma s by gamma w is referred at a specific gravity, that is gs of the solid, or relative thing you can also say. I will be putting all these value here. So I will be getting cd drag coefficient 1 by g vs square is equal to 4 by 3 g gs minus 1. Okay, so after putting the all the after taking this term in the denominator, and squaring taking root on the both side, I will be getting this settling velocity is equal to under root 4 by 3 gd into gs minus 1 divided by drag coefficient. I hope this derivation is very common derivation. You should, I think you should aware of this derivation, and also you should remember this formula, that is what is settling velocity for the given drag coefficient and given a specific gravity. Okay, so this was your formula. So now what will happen that during this, then when particle is settling down, the flow can be of different nature. Now consider that uh, consider that this flow is happening in a laminar flow, or particle is settling in a laminar condition. Laminar condition means one layer is not interfering with second layer. Ignore this thing. I won't discuss why this d should be less than or equal to 0.1 mm. But only one condition for this laminar flow is that the this is known, this is re is Reynolds number. Reynolds number should be less than 1, and the Reynolds number formula is given by density into setting velocity into diameter of particle divided by dynamic viscosity. Remember this thing, dynamic viscosity and kinematic viscosity. You should also aware, you should also know the unit of these two kind of viscosity. Okay, I will ask you to go and search for it. I won't say what it in upcoming question. There is, I have already written the unit, but you should know the unit of this these two things. Okay, so when what will happen that when this Reynolds number is less than equal to 1, then the flow is known as laminar flow. And this for laminar flow, a Stokes law is defined, and a Stokes law is given as CD is equal to 24 by RE, and RE, you know this thing, rho vs d by kinematic viscosity. You can write, means I can write CD in both terms, that is kinematic viscosity or in the term of dynamic viscosity. I will be putting this CD value here, and I will be getting this Vs, the equation for Vs when the condition is laminar flow, and the formula will be given as Vs is equal to Gd square Gs minus 1 18 mu, or 18 mu, or 18 kinematic viscosity. Now remember this, when suppose in your question it is written as the data is given for dynamic viscosity, then the formula will be used will be mu into, in upper side it will be, there will be a multiplication of this density of water. Okay, I hope this is clear. Similarly for this transition flow, when at this condition what will happen that this Reynolds number is greater than equal to, remember this equality, greater than equal to 1 or less than equal to 1000, then this CD is defined as 24 by RE plus 3 by under root RE plus 0.34, or in some book it is also directly written as 18.5 RE 0.6. This is approximate formula. This is also somewhere, means depending upon the type of data or where you are solving one problem, you can use the formula. Suppose if you are solving in a theory, means sorry, in a subjective, you are giving some subjective example, you will be using this equation. There is one example I will say you, but if you are using, if you are giving some gate exam, yeah, some objective exam, you can directly use this equation. Okay, so what will happen that, you know, this CD, I will be putting down, I will be writing down the RE in value of RE, and I will be putting the value of CD here, and according to that I will be finding the value of transition settling velocity when the transition is when the flow is in transition mode. Okay, so this is settling velocity, means particle is from this is tank, our particle is settling from here to here, so that there this is known as settling velocity. For discrete, just remember the common formula is this thing, but for laminar case, the- generally what happens that in each and every system that you will interfere or you will see follow laminar flow, that's why this formula is common, that gds squared gs minus 1 divided by 18 kinematic viscosity. Remember this thing. Then the second thing is scoring velocity. Now what will happen that this was your and I will hope this time I am able to draw it properly. Now consider this is your uh, settling tank. So and the water is up till here. There is one particle here. There is one particle here, and see this particle has tendency to go this side also. The both particle will settle down with this velocity, that is vs. Now just remember that the water treatment is like a, what do you call, a series of unit treatment plant, so water is also flowing in this direction. Okay now, so what will happen that this will have two velocity, two velocity, this it will also move in downward direction and this in this direction. Okay, sorry for the drawing. Okay, so what will happen that this is referred to settling velocity and this is known as scoring velocity, means at what rate this particle is going in the horizontal direction, then that velocity is defined as a scoring velocity, and that is given by 4 under root g, this is gs minus 1 also into diameter of this, that what do we call, diameter of that this particle. Okay, so doing design, when we design this tank, this PST that you have already studied in your lectures, so this the the major role is played by this vs and vsc. We want to maintain vs and scoring velocity in a such a way that all the particles settle down properly and do not go outside uh, this tank. We want this particle to settle down in this tank only, so we have to maintain the horizontal velocity and the vertical velocity in a such a way that as soon as particles enter in this tank, it settle down here. Okay, so generally for any question this value will be given to you, but in general from many research paper or many wastewater treatment plant, they have for they have generalized the thing, and they generally take g as 2.65. This is density and this is kinematic viscosity. Remember its unit is meter square per second. Okay now. Okay. So 1.01 into 10 to the power minus 6 meter square. You can put the value if you know the diameter of your particle. You can find the what should be the scoring velocity and what should be the settling pi continue. Okay. Okay. So this is coming to the second question, which is related to this derivation only. Find the terminal velocity of a spherical particle with the diameter 0.2 mm settling through water. Refer to the data given below. You have been given this data, and you have to find the terminal velocity. Terminal velocity means settling velocity only. Okay. Uh-huh. So the terminal velocity, we know that this is given by Vs is equal to under root 4 by 3 GD Gs minus 1 CD. Now I will be solving. I have to assume that because in the question it's not given that the flow is laminar flow or transition flow. So I will be solving for each condition. So first I will assume that flow is laminar flow, and we know that for laminar flow RE should be less than equal to 1. Okay. So and we already know this CD. This is my formula, and for when and remember in our question the data is given for mu. You see mu that and it has unit of Newton second per meter square at 20 degrees Celsius. So I will be using this formula. I will be putting all this value always and when we substitute this value we will be getting Vs is equal to 0.056 meter per second or 56.2 mm per second. Now I will be checking our assumption. We have assumed that flow is laminar flow, so I will be putting all the value here, and I am getting Re is equal to 14.01, which is greater than equal to which is greater than 1. But for laminar flow, the Re should have been less than 1. Means our assumption is wrong. So this the hence the velocity which we found, that is 56.2 mm per second, is wrong. So now the second condition is this is what I have written. Now we will show iterative procedure iterative procedure to calculate the terminal velocity. Okay now. So actually I have written it wrongly here. It's not iterative procedure. So now see what I have done here. Then I will explain why I have written it wrongly. So for now I have assumed that this will be a transition flow. So this is transition flow means RE should these all equation are used for calculation of RE and for CD. Now what I have done, see, the next challenge was that I have to, in this equation I have to put the value of CD. So for putting the value of CD I have two options, either to use this equation or to use this equation. If I am using this equation, that is CD is equal to 18.5 RE की power 6. So what will happen that if you put this RE value here, in place of RE you will substitute the value and you will calculate the value. You will be getting Vs is equal to 0.0318 meter, and after checking you will be getting 7.93. Means your condition was flow, means your terminal velocity or settling velocity is 31.8 mm per second. So this is not iterative. I have not done any kind of iteration. Like let's assume case one iteration means we are using previous value. So the as I am saying, means for now I have done used this formula, but I could have also used the iteration method. In iteration method, what I would have done, that from laminar flow, from laminar flow I have already found out the value, that is 0.0562 meter per second. So from laminar flow I would have calculated the value of RE that has come out to be 14.05. From here I would have noted down I would have substituted the value of RE, then would have found out the value of CD, and whatever the CD would have come, I would have directly I would have substituted here, and then would have found up my settling velocity. So if you do this iteration means, again you will put the first you will put the value of CD, then you will find the setting velocity, then again you will check the value of RE whether it's coming in the transition phase or not. If it is coming in the transition phase, means obviously for first case it won't be correct, because for RE14 uh, means you will face some problem. I think you will calculate the value of this Vs, then you will again put it here, and then again you will check that whether you are getting your desired result or not, or your or your assumption is correct or not. From suppose if your assumption is correct that this by putting new settling velocity you are getting re less than equal to miss in between less than 1000 and greater than equal to 1, then that is your correct answer. Now just imagine that you are not getting this. Again you will, what you will do that again you will calculate new re, again you will put it here, again you will be getting new cd, and depending upon that you will keep going until your condition is satisfied or not, that is re should be greater than equal to 1 or less than equal to 1000. The moment you got those value, that will be your final answer. So for I have used direct formula which is also correct for solving this equation. When you will put this re cd value here 18 point, it will get complicated, so you can use either directly calculator. Means calculator will also provide this means I have used this calculator. This is fx991es. Here I you can use directly, or you can, based on some assumption, you can also solve this thing. I hope this is clear to you. So I will be going um, to the third question, which is also related to this thing only, related to settling velocity only. So there is a water sample contain two kind of particles, that is of 0.3 mm and 0.4 mm, whose quantity is 40% and 60%, and settling velocity 0.25 and 0.3. Total solid is 500 gram. Design flow rate is 0.3 mm per second. So now you have to find out the horizontal efficiency. So if you are appearing in the gate, this kind of question also has appeared in gate also. The hint you should get from the question is that this design flow is 0.3, and corresponding to the 0.3 the size is 0.4 mm. This is hint given in the question. The first thing you should have an idea that every as the design flow is for 0.3, which is corresponding to 0.4, means the particle having setting velocity 0.3 will settle down anyhow. Miss it has been designed for 0.4 mm particles only. So any particle having 0.4 or larger size will settle down, but for this case the setting velocity is 0.25, means no, it won't settle down completely. Some portion will get settled down and some portion will move away. Okay, so this is what I have written, that overflow rate is 0.3 mm, Vs for 0.4 mm. Particles are also this much, since all the particle greater than this will settle down. Again, and the weight of the particle totally 500 gram. So the 0.4 mm particle would have weight of 300 gram, and 400 sorry, this is typo mistake, this will be 0.3 mm. Okay, just let me correct it now only. So that will have a weight of 200 gram. So till now I can say that all these 300 gram will settle down. This 300 gram will settle down. The question is how much out of 200 gram of 0.3 mm particle will settle down. Then that is given by the efficiency formula, which is settling velocity divided by design velocity into 1000. If I have time at the end of the lecture, I will derive this equation also. How means this is very simple derivation also. Hmm. Miss, you should know this. If you are not aware, you should look at the derivation. If I have sufficient time, I will just describe also what is the how this is derived. Okay. So for 300 particles, all the 300 gram will settle down. For 300 mm particle, the efficiency will be uh, 0.25 into 0.3 into 100, that is 83.33%. Means out of 200 gram only 83% will settle down. Okay, means out of 200 gram only 166.67 gram will settle down. So total settled particle will be 300 plus 166.67, that is 466.67 gram. And you know that total weight was 500. So total efficiency of this tank will be how much has been settled divided by total, then that is 93.33%. So this is the answer of this question will be 93.33%. I hope this is clear to you. If you are not able to understand, please let me know. I will try to explain it again in a, I have tried to explain in a very simple way, but if you are not clear with the idea, means how, what is the thought process behind this question, I will explain it again. So this was question number 3. Coming to the question number 4, which is very easy question. The question is, wastewater has various kind of nutrients present which can be utilized by microbes for cell synthesis. Select the nutrients which are categorized as major nutrients. Remember, remember, out of these 5 options, all 5 are nutrients, part of nutrition. The question is major nutrients. Major means which are helping in the formation of cell, yeah, their survival. You have to mark those questions. But if suppose the question was which are categorized as nutritions, then the all 4 options will be correct. This is just multiple choice question. Okay, now. So this question can be simply, means there is no high-fi logic behind this. This is well-known things that this nitrogen and phosphorus are main component of our nutritions. That's why we use this kind of in our soil everywhere. So for in wastewater also, it's cell synthesis also this is required, that is phosphorus and nitrogen. So this was a direct question, that major nutrition in wastewater is phosphorus, and phosphorus is essential for nucleic acids, uh, phos- phospholipids and ATP. ATP, this is thing which is, you must have read in biological science. Nitrogen is required for protein synthesis. See, other are also required, but their quantities are very less. Okay, so the correct answer will be B and E, that is phosphorus and nitrogen. So this was a direct question. Coming to the fifth question, which of the following is not a step in activated sludge process ASP? There are 4 options. So before answering this question, first you should know activated sludge question. This has been discussed detailed in your lectures, but still this is what I have learned during my, when I was doing my this course during my MTech. Then I have shared that image. So this is a plan of activated sludge process. So what happened that this activated sludge means there means what happened that microbes will eat organism. Remember, this is used in secondary treatment unit. So microbes will eat organic matter present in your wastewater, and it will produce some kind of sludge and all these things. So this process is very slow. Suppose if you leave the wastewater and let the microbes do their own job, it will take very long time. But we know that we have to treat our wastewater very frequently, means in a fast manner or in a very rapid manner, so that it can, so that, but there is no burden, because every day huge amount of wastewater is coming to your treatment unit, so you don't want to waste time on treating single single batch of wastewater. So what happened that to decompose our organic matter via microbes, we activate it by use of some microorganisms. So what will happen that this before this there were certain treatment unit. So water is coming from here, then it will go in this tank, the and after that it will have some kind of aeration, and then it will go in this tank, where what will happen that it is producing some kind of sludge or some kind of it has some active bacteria or active microorganism in it. So what will happen that what we will do that I will take some part of this active why I'm saying active, yeah, why the term active microorganism is used, because what happened that here most of the organism present is there is very active, and that is decomposing organic matter in a very fast way. So what will happen now? Imagine what initially what was happening that ignore this flow. So what was happening that water will come here. There will be some kind of aeration. Then it will go, and then it will get treated, and then it will go through the second unit. Now what I am doing that I am taking some active organism from here, and I am passing here, so that along with aeration some kind of this what do we call decompose of organic matter which is there in the system started to happen here. That's why the term is activated. I am activating my wastewater which for formation of some kind of sludge. So that why and for activating it, what I am doing it, I am taking use of sludge present in here, and that sludge contain active microorganism. So this will enhance, yeah, increase the efficiency of decomposition of organic matter by microbes. So here X is the biomass concentration and S is the substrate concentration. Biomass means concentration of microorganism, and substrate or concentration means concentration of your organic matter. Okay. So there are five options. So I will discuss one by one. So every unit has some here it is showing two units. So I will discuss one by one what are those things. Okay. So the first option was mixing and aeration of mixed liquor. So this is here you can see this is mixing sign. So I will read out the statement which is a standard statement, that is wastewater mixed with activated sludge. I have already mixed it. You can see the activated sludge has been uh, mixed with the incoming wastewater. The wastewater mixed with activated sludge microorganism. This activated sludge mostly 99% contain its microorganism. Undergoes continuous mixing and aeration in the tanks. This promotes the growth and activity of aerobic microorganisms which consume organic pollutant present in the wastewater. Okay, so what is my main aim? My main aim is to decompose the organic matter. So what I am doing that I am mixing it properly and also giving some aeration so that oxygen can be present there. So what happened that this is aerobic, I am saying aerobic microorganism. Remember what is aerobic microorganism. Aerobic microorganism are those microorganism which survive on fixed oxygen, not free oxygen. Aerobic means those who utilize free oxygen, and anaerobic means those who do not utilize free oxygen. Remember, both utilize oxygen only. One utilize free oxygen, and one uses attached or not fixed oxygen. Okay. The second option was settling of the mixed liquor into a separate the sludge. So what? Remember this thing. This is in a conical shape. So what will happen that after decomposition, the set here remember this you I've sent zone settling. Zone settling are hindered settling, no, compression settling. You can say both kind of settling happens here. So what will happen that some particle will get larger and some particle will be small. The smaller be larger will get settled down, and along with settling, it will also take down the bigger particle. Okay. Uh, so so what happened after aeration? The mixed liquid is allowed to settle in the tank or clarifier. So we allow after decomposition we allow the upper particles to settle down in this tank. During settling, the higher particles, including the activated sludge flux, settle to the bottom of sludge, and while the clear water rises to the top. So what will happen that after all kind of reaction, or what do we say, decomposition by organic matter, it will form some kind of flocks, means fluffy things, and it will all settle down, and you will get clear water at the top, which will be passed to the second unit. And what will happen there, the sludge will be taken out from here to the some another chamber or another unit. Anoxic condition of denitrification. So read out this statement. In some ASP configuration, anoxic condition, or that is absence of oxygen, remember this, anoxic means absence of oxygen, are created within the treatment system to facilitate the denitrification, when nitrate is converted to nitrogen or nitrogen gas by denitrifying bacteria. This helps in reducing the nitrogen content in treated wastewater. Remember, our wastewater content a large amount of organic matter, which is in the form of CHN, carbon, hydrogen, oxygen, and nitrogen. So the amount of nitrogen which is present in system is very high. And if you look at the drinking water limit, yeah, discharge limit of wastewater or drinking limit of water, as I am talking about wastewater only, so I will talk about the discharge limit. So as per CPCB, when we discharge our wastewater to river, land, or sea, there is some limitation on how much nitrogen I am throwing in the system. Because if I am throwing too much nitrogen in the wastewater or in water or in land, it will cause eutrophication in the lake or in the river body. I think you are aware of the term eutrophication of the lake. Eutrophication means growth of alga, and that alga consume nitrogen. So what happened that we add some kind of denitrifying bacteria. So that bacteria will consume, what will it will convert this NO2 NO3 minus into nitrogen or some kind of nitrous gas, and that will escape in the system. So the load of nitrogen in the wastewater will be very less, and it can be thrown or it can be discharged easily. So my suggestion to you is just go to the CPCB guidelines and see how much nitrogen in the form of nitrate and nitrite we can throw in our wastewater. So there is some limitation. Exact number I don't know. That's why I'm not sharing it. But our main target is to reduce the nitrogen content. So that removal of nitrogen will also happen in this activated sludge process only. This was fourth option. The fourth option is fluctuation of mixed liquor. So already I have said that in apart from adding microbes, we also add some kind of chemicals. So this involves addition of some chemicals, coagulants or flocculants, to promote the aggregation of fine particles suspended in the wastewater into larger flocks. So there will be some particles, see, organic matter which is there, it will decompose, it will form flocks that will settle down. In spite of that, there will be some suspended particles also, which has not been settled down in settling chamber, exit chamber, so that has been carried out till now. So I have to remove that thing also. Okay. That thing also. So for that I will be using some kind of chemicals, which initially that what will happen that chemical will change the surface property, and by changing the property, what will happen that the adjacent particle will gets uh, uh, attached toward it, and its weight will increase and it will settle down. So out of five option, I have already all the you can see all these were part of this activated sludge process. Then there is come fourth option, that is drying of sludge. So remember what happened, that sludge is produced, the clean water is taken out from up topmost layer to the another treatment unit. The sludge is passed to something else. Okay, to some else unit. So this is not part of activated sludge process. The answer is directly from the here, that is drying of the sludge is not part of ASP. it just generates sludge. Sludge will be handled by some other another treatment unit. So read out this statement. Drying of the sludge is not a step in a traditional activated sludge process. Instead, sludge management usually involves further treatment process such as thickening, dewatering, and some incineration or composting to reduce moisture content and stabilize the sludge for disposal or reuse. So this is function of sludge. Sludge treatment is very different thing. We do not handle it in activated sludge process. Activated sludge process only produce sludge, which is further taken. It's there are several processes involved in how to reuse, yeah, how to dispose our sludge in the environment, or how to use our sludge. Okay, so the correct option will be D. That this ASP is not used for drying of the sludge. Okay, so coming to the sixth question, which is also related to this activated sludge process. So these are formula based question. Every formula is derived. I don't have time to derive the formula, but whatever the formula I will be using here, I will request either to see the lecture notes or to refer some book where this formula has been derived, because in wherever you are studying it or you are preparing for exam, generally they won't be asking question directly based on your formula. They will be checking some concepts whether you are able to use or not. So the best way to clear your concept is that go through the derivation. Do not memorize formula directly. You should remember your formula, but before remembering, you should see the derivation, how that formula is derived. The first question is this: aeration tank in a wastewater plant contain a mixed liquor volatile suspended solid, that is MLVSS, concentration of 3000 milligram per liter. So you can imagine how much suspended solid is there, and that is volatile in nature and has concentration 3, means in 1 liter you are getting 3 gram. Now remember, then when we generate wastewater, it's in 1000 liter. So how much wastewater will, how much suspended solid will be there? The plant receives a primary effluent with biological demand to 208, yeah, 208 milligram per liter. This is another thing, biological oxygen demand, BOD. You should have a, if you have, at this stage you must have an idea of what is BOD. But if you are not aware of what is this BOD, I will request you to go to the previous lecture and go what is this BOD, how this is relevant to this biological treatment, and what is its significance. And the flow rate is 12 mld, that is 12 million liter per day. You can imagine, miss, suppose if a wastewater treatment run for complete 1 day, which is not possible. No treatment plant receive water completely for 1 day. All treatment plant run for some certain period. There is like time duration defined, that this treatment plant will run for this unit to this time to this time. Remember, suppose out of miss suppose it, the wastewater the treatment plant only run for, say, suppose 5 hour. So from this image, from this calculation, you can imagine how much water is coming for the treatment. Okay, the volume of the tank is 1875 cubic meter. Find the F by M. F means food by mass ratio. What is food? Food is your organic matter present in the suspended. A mass is microbes that you are adding in the system. So to treat this, whatever the unit, whatever data is given here, how much mass by food by mass, what is the, see, food is already given to you, and somehow you have to calculate what will be the ratio of this food by mass ratio. Okay, so this was our sedimentation, sorry, this was our activated sludge process. Water is coming here, something is happening here, something is happening here, some sludge is going past, some sludge is being taken out from here, passing it here to activate this process. and many things. Okay, so there are several terms, which terms which is very easy or very frequent. I will be sharing. I will be writing down that formula. The first formula is hydraulic retention time. Means for how much time the water is in this sedimentation tank. That is very obvious thing, that if the volume is V, flow is Q naught, then what will happen, that this thing, what will happen, the the hydraulic retention time will be velocity divided by Q naught, means at what rate the water is coming in the system. Second is substrate utilization rate, means at what rate this substrate, remember what did I say, which one out of these is S or X is substrate. S is substrate, means substrate means how organic matter present in there at what rate that is being consumed. So it will be Q naught S naught minus S divided by Vx. Remember the unit of these these things. The hydraulic retention time has unit of time, that is mean second, day. The unit of this thing will be uh, just you can miss find out, it will be T minus time minus this is your in also milligram per liter, this is in also milligram liter, it is meter cube per day or per second, and it will be meter cube get cancelled out, so unit will be time inverse. Okay, the third is food by mass ratio, sorry for the mistake. Food by mass ratio, the formula is given, how much food is there. Food means organic matter, means how much I am uh, giving it, at what flow the food is coming, that is inorganic matter is coming, and what is the concentration of inorganic matter in the wastewater, divided by what is the mass will be volume of the sludge into what is the x, means what is the um, just remember how I have defined this x thing. X is biomass concentration, remember this F biomass, means in that V volume how much mass of microorganism is present there, that is mass of the, that is mass which we are talking, and you have to find its ratio. Generally when we talk about the ratio, it is a unitless quantity, but remember this thing. Hmm, why it's happening like this, sorry. Sorry, remember whenever we talk about ratio, we see that it has a dimensionless quantity. What this food by mass ratio, you can check out what is the unit of this food by mass. It is Q naught meter cube per second या meter cube time. S naught will be milligram per liter. It will be X will be milligram per liter, and this will be V, that is meter cube. So meter cube will get cancelled out. The the unit of this FYM will be time inverse. Okay, you should remember it is saying ratio, but it's not a unitless quantity, because our mind generally say that whatever is whenever we talk about ratio, that is a unitless quantity, but that is not correct. Okay, so for our question, we have already given everything. We have been provided with every data. Q is 12 mld, that is 12 into 20 power 6 liter per day, that is 12,000 meter cube per day. S naught is also given. S naught is given, that is 208 milligram per liter, that is initial. S naught is substrate, means initial BOD. BOD, how BOD means biological oxygen demand. That is also referred in the term of oxygen, um, presence of organic matter. Then there is X. X is substrate concentration, that is 3000 milligram per liter. Okay, sorry, X is microorganism. Sorry, I said something wrong. and volume already you have given the volume. So you will put all the value. It will be 12,000 meter cube per day, 208 milligram per liter, 1876 meter cube into 3000 milligram per liter. Milligram will get cancel out, meter cube will get cancel out, and after calculation you will be getting your answer. F by m is equal to 0.444 day minus 1. I hope this is clear to you. This is, remember, you can, there is no direct derivation, but there are several things related to this activated sludge process, this substrate utilization. Then there is residence time, mean residence time. Already there is hydraulic retention time. There is another thing, mean residence time. So go and check out those three things. Again, one question related to this thing, that is activated sludge process. Just 1 minute. So there is one treatment plant with flow 4.5 mld. mld we generally pronounce it as mld, that is million liter per day. Influent BD 210 milligram per liter. Aeration tank 3 hours. Biomass concentration in tank is 250 milligram per liter. Quantity of wastage sludge. Remember this thing, sludge 0.05 meter mld. Then there is yield coefficient, which we define how miss is this detail of this yield coefficient has been discussed to you in class. Then there is degradation constant 0 by miss, remember this organic matter will degrade via some order of reaction or by via some rate. So that rate is kt 0.05. This thing has been also discussed in your class. The average time for which biomass stay in the system is 3 days. Remember, the aeration tank HRT is 3 hours and the average time for which biomass stay in the system is 3 hours. These two are different things. Here we are talking about a biomass, how for how much time the biomass will stay in the system, and here HRT means how much for how much time water will stay in that tank. Assume that the authority has enforced a treatment wastewater standard BOD 5 of 20 milligram per liter and suspended solid of 20 milligram per liter. The MLSS concentration required in the system is, so this, remember this thing. I have said every our, what is the, what is my main target in the wastewater treatment. My main target is to dispose our wastewater treatment. So in India there is CPCB, Center of Pollution Control Board. It has defined something that when you are discharging some wastewater, first you have to treat it, and you have to treat in such a way that certain parameters such as BOD, DO, suspended solid, nitrogen content, phosphorus content, everything, pH of the system should be within one limit, and that is known as CPCB limit. So again, this authority or Miss CPCB has. Now suppose you have opened a treatment plant and these conditions are fulfilled. So during the design you should consider that you have to follow this standard procedure, a standard limit, that is before discharging in, and remember there is different limit for different discharge systems. Suppose if you are discharging in river, there will be another standard. If you are discharging in water, it will be another system, another parameter. And if you are discharging in river sea, it will have different parameter. Okay, so you have to find MLSS. MLSS, remember this thing. MLSS is, here we have talked about volatile. Remove this volatile system. Generally what happens is all the organic matter is volatile in nature. All the organic matter contains carbon only. So that's why we use volatile. But generally what will happen that just let me see, it is I think how much percentage, 80% is now this suspended solid will contain both volatile and non-volatile. Combined, we simply say MLSS, that is mixed liquor, suspended solid. Volatile portion is around 80% and non-volatile portion is 20%. The question is to you have to find this MLSS. Okay, means you have to find this X. Okay, you have to find this X. So remember, I will directly go to the formula part of this formula for this equation. Uh, uh, this this was your um, part of activated sludge. Activated sludge. Here you can see that initially it has some S note, X note, C note. Finally it will have some XE, SE. This, remember, they are saying you to mix this thing within permissible limit, that is 20 gram per liter and 20 milligram per liter. So this is formula of MLSS. This can be this can be derived via applying control volume equation. Control volume equation, you all mass sorry, control volume, no, means in control volume you can apply mass balance equation, that is V dc by dt is equal to mass in minus mass out plus minus some kind of accumulation. So if you apply that equation, you can see that at you will be able to find this equation. I will just give you some hint. So consider this is as your control volume. So this mass at q, and now as I am talking about this x naught, so what will happen that mass in will be q into x naught, and mass out will be 1 plus r into q into x, and there is some kind of reaction that is degrading with the first order. Obviously the organic matter is degrading via first order reaction. So you will be substituting mass in minus mass out plus minus some kind of reaction. So here it will be minus reaction only, minus k d into concentration. And if you rearrange all this thing, you will be getting this formula, that is yield coefficient divided by 1 plus kd theta c plus s naught minus s divided by theta c divided by theta. So all this thing is related to this thing, like how much initial volume concentration was there and what is the final concentration in the system. Okay, and again remember this this S naught which we talk is, see, all data has been given. S naught is generally here I have defined. Hmm. S naught is substrate concentration. Substrate concentration means organic matter concentration. So that is also defined as by BOD. Means organic matter concentration is always defined in the terms of BOD. That is BOD. So in sometime in some book you will say that this is this S naught is influent BOD and this S is effluent BOD in milligram per liter. Similarly, this S naught is in sorry. Similarly, this X naught is initial biomass concentration, yeah, effluent biomass concentration, and this is so inflow. I hope you got it what I am saying. Hmm. So for already, so we were in this question. So for this question, everything has been given to you. The rate at which the organic matter is degrading is 0.05 per day. The rate for the time being which this organic this biomass, remember this biomass is staying in the system is defined as theta c is 3 day. The initial BOD which is entering in the system was 220 milligram per liter. The final BOD in the system is 20 milligram liter. So and this theta is equal to 0.125 day. Okay, so I will be putting all the value and I will be getting the value of x is equal to 1982.6. So remember, so you have your initial BOD was 210 milligram per liter and final BOD was 20 milligram per liter. So you have, so to make to get the desired value of BOD set by CPCB, you have to keep your MLSS rate at 1982.6 milligram per liter. If suppose if your this X, that is MLSS coming in the system is very high, means your system, your wastewater treatment, your wastewater plant will fail and it won't perform, and your final BOD will be not 20 milligram per liter, it will be different, and your main objective to treat water treatment will fail. Okay, so this was another question. This was direct formula question. If you have if you are planning for gate, this kind of question is also asked in theory. Also in subjective paper also they ask, but in subjective question they won't be asking this kind of question. So when I was when I was giving my exam during, when I was doing this course during my MTech period, the first question was first to derive this equation. Then there was numerical related to this question, not this directly, but in your competitive exam like any is gate or any ESC exam, you can expect this kind of question. Recently in 2022 2024 also a question related to this equation. It's not that this equation, but something like this has been asked. Okay, and in real world also you should know that you should not use this equation just to pass some examination. You should also understand what is this what is the meaning of this, what is the use of this equation in real world. So this equation is used, you should know this thing, that this equation is just not on paper. People use this equation in real water treatment plant to solve certain kind of problem, like how much, see, we are adding some we are adding some sludge back in the system. So how much sludge I have to add that such that our system is very optimized and it is working in a very well condition. We cannot add as much as we want because it is activating our system. Adding too much sludge can also hamper the functioning of this aeration tank. Now, suppose you are adding too much sludge, so you have to add too much oxygen also. So that will be economically not good thing. It will cost you too much. So you have to use this equation. What will the value of R? R is means how much should be diverted from this tank to this tank. Means what should be the this ascender limit and all these things. All these things did, is done with the help of this equation only. So whenever you see some equation, always try to see what is the real world use of that equation. Means this is what I have been taught in my doing my classes, that just do not read any equation. Do not learn an equation. Try to know what is the real world application of that equation. Anyone can remember the equation, anyone can memorize the equation. The main question is, can you use that equation in real world problem? So if you are, I don't know in which year you are or what you are doing currently, but suppose if you have studied this course, after this course try to visit any treatment plant and see does whatever have you learned from that course is being that is being followed in that treatment plant or not. So this will be a good experience. Either you can apply down to any treatment plant as from as a part of your internship or just a small visit. So you will see that people are using this kind of equation, whatever I have said initially, this grid chamber. So it was my privilege to visit. When I was doing this course, after that this course only, I was we were allowed to go to visit one. Currently, I'm in Kanpur, so there is one area named Jajamao. So there is a large treatment plant. So we were there. We were able to see all this treatment unit there. Okay. So coming to the eighth question. So see, this question is from generally when people are framing question, they are using means real data. So this is a treatment plant which is in Simla. So elevation of the city is also remember there will be many data in your question. All those data won't be used. Just remember this thing. Elevation of city from mean sea level is 258 meter. Annual average temperature. Remember design temperature is 28 degrees Celsius. Consider the standard oxygen rate 36 minus. Remember in this activator sludge we were rotating now. So we have to provide some oxygen at sufficient rate. It's not that we are providing too much oxygen or very low oxygen. Everything, every unit should be very prescribed. Like this much oxygen, it has to be. This much oxygen has to be given to that system. Okay, so that's why this term is defined that considers a standard oxygen rate. Then there is two term alpha, beta, and F. I will discuss during this that question. Then concentration. This is saturation concentration at 20 degrees Celsius, 9 gram per liter. Then a standard STH is something defined which I will discuss in the upcoming. Then the pressure is this 140 kPa, that is or 96 kp. Hmm. Uh, I don't know. I must have written it some mismatch. Then oxygen transfer rate is 19% Cl. Calculate the average oxygen. Why I'm miss remember this data. There are many things. If you have gone through the lectures, you must have got what are those data. If you are not gone through the lecture, just wait. I will explain what are all these terms are. Okay. The, the question is to calculate the average oxygen transfer rate in the aeration tank. Aeration tank. So remember, already I have discussed this thing. The first question is why there is a need of oxygen. So I will read out this statement and then I will explain it. The organic carbon compounds consumed by microorganism. I already said that my wastewater contains some organic matter and it is being consumed by microorganism and it is converted into carbon dioxide and biomass. Okay, part of this biomass is oxidized by organism to carbon dioxide. Yeah, energy produced through the oxidation of organic matter to organic oxidation of organic carbon to carbon dioxide is driving force for microorganism and production of new business. So what will happen that um, there is this statement contain many things. So what will happen? What happened that remember at t is equal to 0 at t I will write yes, consider consider this thing. Initially at t time you have added some microorganism in the system. So what will you know that its population will grow with time. So for growing it needs some energy and food. Sorry, it needs food, and food, what will happen that this food will give some kind of energy to that microorganism, and that energy will be used to survive and to reproduce. So what will happen that the thing which is here I have written is that the organism will consume this microorganism will consume this organic matter, and the energy produced via that consumption will help in production of new biomass. So what will happen that initially you must have read about this biomass curve. So what will happen that initially um, I will add some microbes So it will start decomposing this microorganism, yeah, organic matter in the system. Then what will happen, that energy will be produced, and this energy will help in the growth of that in the growth of that microorganism, and in that way it will achieve some its population will grow, that is and after some time what will happen, that all the food which was there in the present in the system, it will finished off. So there is no food, no production of energy. So what will happen, that remember, this is population of this microorganism and number of microorganism. So what will happen, that there is no food. So what will happen, that biomass or concentration or the population of microorganism will go down. So this is written here. So in all these things, two things is important: this presence of this organic matter, and the second thing is oxygen required. Oxygen is the, I'm using technical term, that is electron acceptor. So if you will write the equation, when we'll be writing the equation, remember this is uh, a very simple form of a organic matter, that is C5H7O2 and N. Oxygen is there. Obviously there is no need, there is no way to store microorganism, but you can imagine that there is microorganism. So with the help of oxygen, the microorganism, this organic matter is being degraded. It is forming this CO2, water and ammonium, ammonia, ammonia you can say. This is ammonical nitrogen, and some energy will be releasing. This energy will be help in growth of microorganism, and the CO2 and H2O will be discharged in the surrounding. So miss the main thing that is to be learned from this thing is that from this topic is that uh, uh, there's some oxygen has to be provided, so that the in the presence of that oxygen, this macroorganism will act on will degrade this organic matter in the system. So there is then there is how oxygen is being given in the system, then that is controlled by theory of aeration. So that is given by Henry constant. You must have already about this Henry constant, Henry law, sorry, Henry law. So what will happen, that there is oxygen in atmosphere, and it will go in the system, that is in a liquid phase, only if sufficient pressure is given. Huh. Sufficient pressure is there, means partial, if suppose sufficient partial pressure is there, that any liquid will dissolve in that, any gas will dissolve in that liquid. This is general concept of Henry constant. So here we also use the concept of Henry constant only. Okay, so remember this was your tank. Okay, this was your tank. Here water will be from air, water will be coming in the system, and the liquid oxygen will may also live in the system. So the rate of oxygen which is in there in this liquid phase will depend upon this rate of oxygen absorption, that is on K1, and the rate of oxygen stripping, that at what rate the oxygen is leaving out the systems. Remember, if you are not able to understand it, no problem. It's like it's very simple also. There is no hi-fi science. In your 12th class, or you must have read about this simple thing, but we are using that concept to derive that how much oxygen is required in my system. Okay, and I think this has been discussed in your lecture also. Actually, I am not gone through the lecture, but this thing has been discussed in your lecture. So rate of absorption will be K1 into P, partial pressure of oxygen, and the rate of oxygen going outside the system will be minus K2 into oxygen in the liquid phase. At equilibrium, what will happen that these two will attain equilibrium. Whatever is going out in the system is, or for this equation you can see that the concentration of this will be equal to the concentration of this. So oxygen in liquid phase will be oxygen in the, that is present there, sorry, outside oxygen. So you can find out the what will the partial pressure required for in the terms of equilibrium constant of K1 K2. So this is very simple. uh, Again, after substituting all the value, I can derive this equation, but I'm not going to discuss because you can see. So after substituting the different value, the rate at which the oxygen should be given in your oxygen tank, aeration tank, is given by KL A by V. uh, Oxygen in liquid at saturation. Remember that oxygen OL2 means concentration of oxygen at saturated limit minus concentration at any time is given by this thing. And that can be also defined as this thing. Okay, na? KL into A. KL means this ratio is, defined as KL K1 by K2. Okay. So what happened that with time our aim is to saturate our oxygen so that sufficient oxygen is present in the system that can decompose our organic matter present in the system with the help of microorganisms. My main target is that thing only. Okay. So if you reframe the formula, uh, so you will be getting this equation, that is C average. C average is equal to this term, and yeah, average oxygen transfers will be a standard oxygen transfer into this term. And again this has been derived with the help of your mass balance equation only. If you are putting all the value that is given to you, you will be getting that the whatever they were asking, that average, um, this average oxygen transfer rate, that is AOTR, is given by this equation. Okay, that is AOT is equal to this standards. Remember first, actually before finding this actual average we have to find a standard, and that is given by SOTE, and that thing is already given to you in your question. SOTE is equal to 36 point, see, where standard oxygen transfer means this is oxygen standard oxygen transfer rate, that is 36.5. From this given data you have to find this average oxygen transfer. Okay. uh, I hope this is clear to you. This was also a direct formula based question. Its derivation, how do this derivation, how the use of average concentration and the standard saturated concentration is used for finding this AOT and all these things. Remember, I feel this is you might feel that I am escaping. Actually, I cannot explain this thing in 1 hour. This is a whole thing. How this beta came, alpha came, what is this F, then this degradation constant and all these things. This is very lengthy. So I will suggest you to go some standard book or go to the lecture. You will be able to see this equation and you will be able to derive it. You will be able to explain, or you will be able to understand in a better situation. Okay. So the coming to the next question, that is second. Hmm, hmm, The question is the composition of total gender nitrogen in the domestic is expressed in milligram as nitrogen. Which is the result of the addition of. So remember, I have already shown you that this is general form of organic matter. So this is nitrogen. So this nitrogen I am writing in this form, but what will happen that your nitrogen may occur in different forms also. Maybe it will be in simple NO2 nitrate form, yeah, ammonical form. Ammonical means these are different oxidation depending upon the pH, depending on the oxidation number, depending on the stability. Nitrogen can exist in many forms, that is NO2 minus, NO3 minus, ammonical nitrogen, yeah, simply nitrogen gas. It depends upon. So they are talking about this total Jandal nitrogen. So remember the Jandal is a name of scientist. He has developed a method to determine the nitrogen present in the system, that is known as Jandal flask method. So there is a, if you have gone through the laboratory, you can see that there is a tube which is referred as Jandal nitrogen tube. So in that tube this experiment is done. Then that's why this name is total Jandal. The question is now, this can this Jandal nitrogen can measure all the nitrogen present in the system, all form of nitrogen in the system? No, it can measure only two forms of nitrogen that is present in the system. So I will explain one by one. So first I will discuss about the presence of the nitrogen. Okay, now nitrogen is present in water, wastewater, and industrial wastewater sample in various concentration and various forms. Means nitrogen, see, nitrogen is everywhere because our atmosphere is majority of atmosphere is made of nitrogen. So what will happen that any form of nitrogen, different form of nitrogen will be either present in water, wastewater, or industrial wastewater. So first, if we talk about the surface wastewater, what happens that in surface wastewater, nitrogen is in form of nitrate only, that is NO3 minus. So there is permissible now. We know that nitrate is present in our surface water, and that surface water is either used for drinking purpose or irrigational purpose. So this nitrate should not exceed a certain permissible limit that is also defined as per IS code. So if you are drinking one water, make sure that nitrate content in that water is within the permissible limit. In groundwater nitrogen, remember, this I have talked about the surface water, that is river and all these things. Then there is called underground groundwater sample. Groundwater, that is aquifer. In aquifer, the nitrogen is present in both form, that is NO2, NO3 minus, and NO2 minus, that is nitrate and nitrite. In raw wastewater or in wastewater contaminated with domestic and industrial water, nitrogen is mainly present as ammonical nitrogen. That is in form of ammonia, NH3. It will consume one H and it will form NH4 plus. Or organic nitrogen means this nitrogen will attach with some of the organic matter. Remember, this is a organic nitrogen. This thing here, this was simply, we know that some CH4 is there. If some nitrogen will come, it will form something, then it will call organic nitrogen. So this nitrogen is attached to this part, means this is kind of organic nitrogen. Okay, so in wastewater this nitrogen will be either present in this nitrogen form, organic form, or ammonical form. The two type of nitrogen measurement are performed on wastewater: a ammonical nitrogen and general nitrogen. Remember, now what will happen that uh, mm, I have to determine this. Generally, this is already established. Okay, now like in wastewater, ammonia. If there is nitrogen, it will be either in form of ammonical form, or either it will be in form of or nitrogen, organic nitrogen. Now my target is to measure that nitrogen. See, there are several things, but these are also we have to measure that nitrogen present in the system. So this gender I was telling about this gender method now. So what will happen that mhm. So the question of answer which was asked, that what is the what will be the TKN or total general nitrogen? It will be summation of ammonical nitrogen plus organic nitrogen. But the point which I want to discuss here, apart from this, what is general nitrogen, is how we measure nitrogen in the system. The process is general nitrogen. So what will happen that we use some kind of reagent and known as Nessler reagent and all these things. So in a sample, so what will happen that initially ammonical nitrogen present in the system. We take our sample. Means there is different procedure. I will suggest you to read out in the some standard book, like a standard book is some standard experimental producer procedure, that how this general method. But remember this general, whenever they are talking about general method, they are just talking about these two form of nitrogen, that is ammonical nitrogen and organic nitrogen. Okay. The last question is, which of the following factor affect the efficiency of coagulation waste sedimentation in wastewater? Okay. So I hope you are clear with this, the term coagulation of flocculation. Okay now. So I will just, I have not written in the PPT, but I will just read out what are those things which is generally used in our treatment plant. Okay now. Where did it go? So what happened that this, there is two thing in the system, two thing in our wastewater. First, we coagulate our system. Coagulation with the help of some chemicals such as alum. We use that. What will happen that it will form means coagulation, and there is flocculation. Means that is also simple thing. The basic in that case also we add chemicals only. The basic difference is that when we coagulate our system, we mix rapidly, so that a proper interaction between the suspended particle, a particle which is there, and a proper chemical reaction can happen. That's why. And then when we flocculate our, when we do flocculation, we gently mix, because what will happen that after coagulation, majority of your particle will have been settled down. In flocculation, what will happen that we slowly add chemical and we slowly add mix it, so that the particle which were not able to settle down due to coagulation may also get settled down. Just let me recall, did I say right or wrong? I said right only. So remember one thing, the main prospective main aim is that is coagulation is that we have to add some chemical, it will do some reaction, it will it will change the property of the system and it will flocculate. So how means how how this coagulation waste sedimentation is affected. So there are four options: pH of the wastewater, temperature of the wastewater, surface overflow, or all of the above. So I will discuss one by one. The first is pH of the system. So remember, if you are following my discussion, I have clearly mentioned, I have I have mentioned the term pH around 3 or 4 times whenever I was discussing ASP thing, yeah, settling thing. The pH of wastewater influences the charge of the particles in the suspension and effectiveness of coagulants. Optimum pH conditions are required for effective coagulation and flocculation to occur. Remember this thing. This is straightforward. Any reaction in the system or in nature, not, I'm not talking about this wastewater, is dependent upon the pH. If pH is favorable, then that reaction will happen. If the pH is not favorable, then that reaction might not happen. It is also defined in the term of thermodynamics also. We generally say that for any reaction to follow, the thermodynamics has to occur. So in this case also, what will happen that depending on the pH of the system, different kind of chemicals are added. So different type of coagulants that is generally added are alum is there, then there is this thing, another what we call hydrated ferrous sulfate, then chlorinated ferrous sulfate. So what will happen that we cannot add, so we you should have an idea that which kind of coagulant you have to add on which condition. So the addition of different kind of coagulant depend upon the pH of the wastewater. So generally what happens then when the pH is around pH is greater than 9.5. Suppose if you have a wastewater which has a pH of pH greater than 9.5, then it is said that you have to add this ferrous sulfate thing. But when pH is around 3 to 6.5, then it is said that you have to add ferric FeCl3, means ferric iron 3 chlorine. Okay, na? And when the most common coagulant which is used is alum, who has pH range of around optimum pH range of around 7 to 8. Suppose if you have any wastewater which has pH of around 7 to 8, you can add alum. Okay, so so coagulation is depend upon the, now suppose imagine you are using a wastewater has pH of around 9 and you are using alum, so that alum won't work, that is wastage of money. So you have to be specific, you have to check your pH of the wastewater, then according the condition of the pH you have to add different kind of waste alum, sorry, different kind of coagulant. Okay, just let me check what is the optimum pH for this alum thing. Optimum pH of the alum is 6.5 to 8.5. So now imagine if you have a wastewater having pH 9.5 or 10, you cannot add alum. Alum means you are Al2SO4 dot 18H2O, that is normal alum fit key also say. So I hope this is clear to you that we cannot add anything, yeah, anywhere. Okay, the temperature of the wastewater, again this thing, thermodynamics. For any reaction to move forward, there should be some thermodynamics involved in it. First of all, read this. The temperature affects the rate of chemical reaction involved in the coagulation and coagulation process. Generally, higher the temperature can enhance the kinetic of coagulant interaction with the contaminant and improving the efficiency of sedimentation. So this is true, like true in the sense like higher the temperature, what will happen, the rate of the kinetics will be higher. Temperature is higher, there will be more randomness in the system, there will be particles will be interacting with each other in a very finer way, in a very proper way. Proper interaction will happen, means proper coagulation will happen, the larger particles will form very easily. So that's why the coagulation is also dependent on the temperature. Surface flow rate. So remember what is the surface flow rate? Surface flow rate that I have discussed with the help of one diagram. Hmm, whatever, this is pain. Surface overflow rate. SOR, that is also referred as SOR. Remember this thing. Remember the over surface overflow rate. I am not talking about in this direction. Okay, now I am talking in this direction. Whenever we talk about SOR, that is surface flow rate, means at what rate or settling velocity. See, SOR is design rate. Means when you are for see, we don't know is means during design we use the term SOR, because in your wastewater there will be different kind of particle. Every particle will have different settling velocity. So settling velocity of wastewater is never defined. Settling velocity of particle is defined. But during design, we define one term, that is surface overflow rate, and that surface overflow rate define a particle size. Like uh, During that example, you have seen that SOR was 0.3, and for particle size of 0.4 mm, SOR settling velocity was also 0.3. So by defining SOR, we also define that particle having that velocity will always settle in your system, and a particle whose size is greater than that particle will also settle down. So overflow rate just define that whether that particle that is coming in the system is settling down or not. Okay. So the SOR refers a rate at which water flow out of the sedimentation basin per unit area of the basin surface. Controlling the surface of the crucial ensuring proper settling of the flux, preventing the carryover of the suspended solid. I think I have written it wrongly here. This is wrong. This is not correct. When we talk about SOR, when we talk about SOR, we do not talk about this basin thing. Okay, now remember what I have told you. SOR means the flow at which this particle is getting settled down. So that should be sufficient. That will make sure that when particle is combining with the yeah, making flocks, they are making proper in they are forming a larger flocks, and that can settle easily. So hence I can say that therefore all factors, that is pH, temperature, and surface flow, can influence the efficiency of coagulation based sedimentation in wastewater treatment. Hence the correct option is D. So that was the last question. So there was something which I said that I will discuss in the last, that is derivation of this thing. Before discussing that, there is thing efficiency is defined by BSY VP not. So currently there are only two students. So if you have any kind of doubt, you can ask now, because this this is very simple, because I will be here till 9 p.m. 7 minutes is left. So if you want to ask something, you can ask. Archana Kumari and Prashant Bhattacharya. Okay. Uh, also, just I will go through. I will just take 5 minutes. 5 minutes, or what should I do? Oh, so I just writing on this thing is very difficult for me. Just try to. Now see, pain. Hmm. So remember this thing. This is your tank. Now imagine that uh, W weight of suspended solid is coming to in the system, and the settled one is WS. WS. Okay. So the efficiency will be given by what? Efficiency will be equal to. Sorry, see, I'm writing on this directly on the laptop. That's why I'm writing in this way. But I hope you will be able to understand it. The efficiency will be given by whatever has settled divided by whatever is the weight of suspended solid that has come into the system. So this is the general formula for the um, so this is the efficiency formula which is given. Now how to get from here to here to here. So now just imagine two things. If now imagine this was your height of the tank. This was height of your tank H, capital H, and the settled solid which has settled in the system has around height a small h. Okay, so uh, when all suppose you have designed your design your settling time in such a way that all the solid which will be coming in the system will will settle down in the system, then that will come that will occupy a length of h. Now as your miss some limited amount of particle is settling down in your system, then it will only consume one height h. So w miss w is equivalent to capital H. Okay, and this ws, that is a small ws, will be equal to, if we want to write in the term of this h, so what will be, it will be w by factor by a small h by capital H. Okay, capital H. Now what will happen that I will put this w, I hope you have got this thing. If everything has been settled, it would have occupied h, but it has only settled only some amount, then it has occupied a small h, and that a small h can be miss that a small weight can be expressed in the term of this thing. So I will be putting this value here. So what will happen that this w and this w will get cancelled out, and your efficiency will be turned out, sorry, and your efficiency will be equal to uh, uh, a small h divided by capital H. Okay, capital H. Now just remember this a small h is corresponding to what? Particle mm, settling velocity of that particle, and this is our design. This is view settling velocity means this is our design. This was for our design velocity, but the time required for both the settlement will be same, that is detention time. Means detention time for the both the particle will be same now. So and we know that velocity is equal to distance upon distance upon time, distance upon time, distance upon time. So this a small h, this a small h will is settling with the settling velocity of that particle, that is vs. Then this a small h will be written as vs into detention time, that is dt. And this capital H is when the velocity is design velocity, that is also known as overflow velocity, which I was saying in the last time, and that is also taking same time, that is dt. Okay, this will this will get cancelled out, and you will be left out with the equation, that is efficiency is equal to vs by v naught. Okay, I hope this is clear to you. If you have any doubt, you can ask, or it's 9 p.m. You can leave the meeting. If you have any doubt, you can ask the question, or you can leave the meeting. I hope I was able to explain all the things which you wanted to see. And this video will be available on the YouTube channel. Just I will share the link. Discard. I will share the link. You can check it out. Where is chat? Chat is here. Oh, we have already. Then no point of sharing this. Okay, Tata.